Well, hello, dear friends. So begins lesson 3 of combinatorics, where we're going to actually talk about this word combinations. Now, the first two lessons that we've done, we dealt with the fundamental counting principle, and then we dealt with permutations. But really, we were dealing with arranging things where changing the order produced a different result. Okay. Remember, I said something to the effect of, if Sally and Timmy and Val are standing in a lineup and it goes Sally, Timmy, Val, and then in another lineup it goes Val, Sally, Timmy, then that's a different picture. That's a different lineup. Okay. If I had apples and pears and bananas and I was throwing them into a bowl to make a fruit salad, whether I threw the apples in and then the pears in and then the bananas in, or I threw the bananas in and then the pears in and then the apples in, does that ultimately change the fruit salad? No. Okay, that's the big difference here. The changing the order did not produce a different outcome. It didn't produce a different result. Okay, so again, you're going to hear teachers all the time say, does order matter? Does order matter? What we mean by that is, if I change the order, would it produce a different result? If your answer is yes, it would, then it's a permutation, which is what we've spent the last 2 days, day and a half, 2 days talking about. If your answer is no, it won't change the outcome, now that's a combination, and that's what we're going to deal with today. Now, the happy note is it's just another button on your calculator, and it's another formula that's given to you on your formula sheet. Okay, so your biggest thing you have to get your mind wrapped around is deciding when you read a question whether it's a permutation or a combination. Once you've decided that, dealing with it, it's going to feel very similar to how you've dealt with it for the last 2 days. Okay. All right, so we'll start with this little investigation. So a combination is a selection of objects in which order is not important. How many 3-card permutations or arrangements can be made from the 10, Jack, Queen, King, and Ace of Spades? Okay, so I'm giving you 5 cards to play with. I want you to create a 3-card hand. Okay, if this was a permutation question, we would look at that and say, oh, okay, then it's going to be 5 permute 3, and the answer is going to be 60. Now, obviously, the answer is not going to be 60, but I want us to try and figure out why. Okay, the problem is this. If I had a Jack, a Queen, and a 10 in my hand, or I had a 10, a Jack, and a Queen in my hand, that's not a different hand. Okay, so the order of how those cards are placed in my hand doesn't actually change the hand that I have. Okay, so what I want you to do is I want you to try and draw them out. Okay, so just like we did yesterday with the green chairs and the blue chairs, I want you to see how many you can come up with. Okay, so pause me for a sec and try that. Okay, glad you're back with me. Here they are. Again, I'm just going to shut my video down for a second so that you can see them all. Okay, so these are all the arrangements you should have gotten, and in total, you should have seen that there are 10 different hands there. Okay, so as you're just double checking that, again, I'm going to say if it was just a straight up permutation, that was 60, but then we actually ended up with 10 different hands. So we have to try and figure out how we go from 60 to 10. Okay, and the way we do that, essentially, it's exactly like we did yesterday. Think about yesterday, I kept saying we have to divide out the arrangements that don't do anything, right? When we had 3 identical green chairs, we had to divide out, so divide by 3 factorial for those 3 identical green chairs. And then we had 2 identical blue chairs, we had to divide out 2 factorial for those 2 identical blue chairs. In this one, I have 5 cards, so that'd be 5 factorial. But once I have the 3 that I'm doing, arranging those 3 doesn't change anything. So I have to divide out the 3 factorial arrangements that don't do anything. Okay, so in any given 3-card hand, the number of permutations of that hand is 3 factorial, but it wouldn't change the hand and therefore needs to be divided out. So we end up with the number of combinations is the number of permutations divided by the number of permutations for the 3 cards that you've already now selected, okay? All right, so as I said, it is a formula. It's very similar to the permutation formula. What I want you to notice is this right there would have been the permutation formula. So really all we do with the combination formula, and this is kind of exciting if you can visualize this, is we take the permutations and we divide out the number in our hand, essentially, that once we now arrange what's in our hand, it doesn't change what our hand is. Okay, so we're dividing out the permutations that don't change anything because the order doesn't matter. Okay, now this is also on your formula sheet. And you do need to recognize this. I have seen questions on diplomas where they'll test you on this. It's a little bit of an older school way of writing it, but you do need to recognize it, okay? So just be careful on that one. So it is also a button on your graphing calculator. For Casio kids, if you have the probability menu open, it's just going to be F3. TI kids, you go into your probability menu by pressing math and then probability, and then you'll see that it is option 3 for you as well. Okay, so here I go talking about gambling again. I talked about gambling in the last class too. Okay, determine the number of possible lottery tickets that can be created in a Lotto 649. Now, the reason Lotto 649 is named Lotto 649 is because you're choosing 6 numbers from the numbers 1 to 49, okay? The order of those numbers don't matter when it's drawn, like whenever they draw these things. When I was little, it used to be in like these big balls, and all these balls would be flying around in a big air bubble type thing, and then the balls would pop out, and some guy dressed up in a bunch of glamoury, blingy suits would name off the numbers. Anyway, now it's all computer generated. But you're picking between the numbers 1 to 49. So there are 49 different things to select from, and then you're choosing 6 of them. The order doesn't matter, so it's a combination. And so you'd be looking at 49, choose 6. Now, type that in your calculator, make sure you're getting the same answer. But essentially, you're getting just under 14 million, okay? So 13,983,816. There are 13,983,816 ways to draw 6 numbers from the numbers 1 to 49, which means you, if you play the Lotto 649, have a 1 in 14 million chance of winning. To put that in perspective, you have a 1 in 3,000 chance of getting hit by lightning. 1 in 3,000 chance of getting hit by lightning, 1 in 14 million chance of winning the Lotto 649. You are way more likely in your life to get hit by lightning than you are to win Lotto 649. So save your money. All right. In how many ways could you create a playlist of 17 songs to be shuffled out of a possible 38 songs? So I have 38 in my selection pool, just like I was talking about in permutations. But because it's shuffling, the order of how I select doesn't matter, and I want to select 17 of them. So it's 38, choose 17, and that's 2.88 times 10 to the 10, okay? 2.88 times 10 to the 10. Okay, given a standard deck of cards. Now, before you get kerfuffly on me, remember when I started talking about the alphabet, we don't even expect you to know how many letters are in the alphabet. That's something you could ask, okay? A standard deck of cards, this is the information on a standard deck of cards. You have 52 cards in a deck. There are 4 suits of 13 cards each. There's 2 red suits, 2 black suits, and the face cards are considered the Jack, the Queen, and the King, okay? All of that information would be given to you. It would never be something that you have to know, okay? You can always ask about that. So how many different 5-card hands are possible? Well, I have 52 in my selection pool. I want to select 5. So that would be 52 C5, which is 2,598,000 960. So if you think you're going to make a career out of card counting when you're playing poker, I wouldn't bother. It's very, very difficult. Okay, how many would be all diamonds? Okay, so diamonds is one of my suits. So there are 13 cards that are diamonds. So that means now my selection pool goes down to 13 because I only want diamonds. Okay, so there are 13 diamonds. I want to select 4 of them. So that'd be, sorry, 5 of them because it's a 5-card hand. I just read that wrong. So that'd be 13 C5. Okay, which is 1,287 ways to get a 5-card hand that are all diamonds. Okay, how many will there be 4 black cards and 1 red card? Okay, so again, remember the wording that we've been kind of discussing here. Here you have the word and. When we have the word and, I need to multiply the 2 items together because both have to happen. I need to have 4 black cards and I need to have 1 red card. Well, how do I get 4 black cards? There are 26 black cards. So I have 26 in my selection pool, 26 choose 4. Then I have 26 red cards and I want to choose one of them. So I would end up with 26 choose 4 times 26 choose 1. And that is 388,700. Make sure you're doing this in your calculator as well and getting the same answers as me. Okay, how many will be exactly 3 kings? Now there's some interpretation that you have to have here. I need a 5-card hand. Exactly means no more, no less, which means in my 5-card hand, I need exactly 3 kings and 2 non-kings. You have to be very clear about that because there's still another king floating around in that deck and you don't want it if you want exactly 3 kings. So there are 4 kings in a deck. 4 choose 3 will get me 3 kings. Then I have to ask myself, okay, how many non-kings are there in the deck? Well, if there's 4 kings in a deck and there's 52 cards, there are 48 non-kings, 52 minus 4. Okay, so there are 48 non-kings and I want to draw 2 of those to complete my 5-card hand. So 48 choose 3 times 4 choose 3 times 48 choose 2, and that would give me 4,512. Okay, how many will be 5 cards of the same suit? Well, I have 4 suits, so I want to pick one of them. I'd be 4 choose 1. And I have 13 cards in a suit, and I want 5 of them, so that'd be 13 choose 5. So 4 choose 1, that gives me one particular suit, and then in the 13 cards that I have, I want to pick 5 of them. Okay, my buddy Stephen Nick are back. A committee of 7 people must be formed from a pool of 12 people. Now notice, we did not put unique roles on this. We talked about committees in the last lesson, but they had unique roles. We were talking about presidents and secretaries and treasurers and researchers and scientists and everything else we were talking about. If there are no select or no specific roles, then committees just become essentially this blob where the order of who's in the committee doesn't matter, right? Whether I go into a committee and then you come into the committee, or you go into the committee and then I come into the committee, it's still just me and you in the committee, okay? So the order doesn't matter. So how many ways can this be done? Well, that'd be 12, and I need 7 of them. What if Steve and Nick must both be on the committee? Well, there are 2 Steve and Nicks, and I want both of them, so that's 2 choose 2. Then there are 10 other people, and I need 5 more people. So 2 choose 2 times 10 choose 5. 2 choose 2 gets me Steve and Nick. And then there are 10 other people, and I need 5 of them to round off my 7-person committee. What if neither Steve nor Nick are on the committee? Well, there are 2 Steve and Nicks, and I want none of them, right? So that'd be 2 choose 0. Then there are 10 other people, and I still need 7 people on my committee. So that ends up being 10 choose 7, which is 120. And we talked yesterday, or in the last lesson, whenever you watched the last lesson, We talked in the last lesson about the fact that, yes, to choose 0, just like to P0, is a 1. So mathematically, it doesn't change the outcome of this if you had just said 10, select 7. But visually, it shows us that you know how to deal with Steve and Nick, okay? Okay, so now we're going to talk about at least and at most questions. These questions require you to add all the possible cases together. So a committee of 5 is to be formed from a group of 4 teachers and 7 students. Determine the number of possible committees that can be formed that require at least 3 students. So we're looking at this word at least. At least means I could have 3 students, I could have 4 students, or I could have 5 students, okay? 3 students, 4 students, 5 students. Now, you have to interpret that though, because I also still need to make a 5-person committee. It says a committee of 5 is to be formed. So 3 students actually means 3 students and 2 teachers. That's how I get a 5-person committee there. And 4 students means 4 students and 1 teacher. And 5 students means 5 students and no teachers. Okay, so now I have 7 students to select from, and I have 4 teachers to select from. So this scenario here would be 7 choose 3 times 4 choose 2. This scenario here would be 7 choose 4 times, how many teachers do I have? 4. 4 choose 1. And then I have 7 choose 5 times 4 choose 0. Please, please, please take a second and put this in your calculator. Make sure you are arriving at 371 so I know that you are good button pushers. Okay. From a deck of 52 cards, a 7-card hand is dealt. How many distinct hands can be formed if there are at most 6 black cards? So at most means I could have 0 black cards, I could have 1 black card, I could have 2 black cards, 3 black cards, 4 black cards, 5 black cards, or 6 black cards. Then you'd have to break that down and say, okay, no black cards really means 7 red cards because it still has to be a 7-card hand. And then 1 black card would have to have 6 red cards and 2 black cards would have to have, okay. So this gets really, really confusing is what I want to kind of show you. If you want to do it that way, totally fine. Go ahead. I don't want to do it that way. I want to think more about the complement here because if I think about at most 6 black cards, the only thing I don't want is 7 black cards. So I think it's easier to take the total here, which would be how many 7-card hands can I have, which would be 52 choose 7, and subtract the only thing I don't want, which is 6 black cards, which is 7 black cards is what I don't want. So then if I subtract out the 7 black cards, what I'm left with is at most 6 black cards, okay? So I'm gonna take the total and minus 7. So the total was 52 select 7, and then at most 6 black, or sorry, shoot, I keep backing that up. I don't want 7 black cards. I'm sorry about that. So there are 26 black cards to choose from. Having an all black card deck would be 26 choose 7. I'm subtracting that. And so that leaves me with 133,126,760. Okay. A student council of 5 is to be formed from a selection pool of 8 grade 12 students and 9 grade 11 students. How many committees will have all grade 11 students? So that means I have 9 and I want to select 5 of them. There are 8 grade 12 students and I don't want any of them. So 8 select 0 is my grade 12s and 9 select 5 is my grade 11s, and that totals 126. At least 4 grade 11 students. Well, I can only have a committee of 5, so that's 4 grade 11 students or 5 grade 11 students. That's what at least means, right? So 4 11s and 1 12, or 5 11s and no 12s is essentially what we're going for. So that would be 9, choose 4, because there was 9 grade 12s. Sorry, there was 9 grade 11s, and then 8 grade 12s, and I'm choosing one of them. Then 9, choose 5, because there was 9 grade 11s, and I want 5 of them in this scenario, with 8 grade 12s, and I want none of them. Okay, because I said or, it's 2 separate cases, and I add those cases together. That's why you see an addition sign here. Plug that into your calculator, and you should get 1,134. Okay, at most, 2 grade 12 students. So at most means I can't have any more than that. Well, what can I have then? I can have no grade 12s, I can have 1 grade 12, or I can have 2 grade 12s. Okay, so no grade 12s really means 5 grade 11s. So I said no grade 12s with 5 grade 11s. Or, so I'm going to add the next case, 1 grade 12 with 4 grade 11s, or 2 grade 12s with 3 grade 11s. So I unpack that. No grade 12s would be 8 choose 0 times 9 choose 5 for the 11s. Add to that 1 grade 12 with 4 grade 11s. And add to that 2 grade 12s with 3 grade 11s. Put all that in your handy dandy trusty dusty calculator, and you should get 3,486. All right, how many ways can a tournament be set up if there are 30 teams and every team must play each other once? How many teams does it take to play a game? 2. Whether team A plays team B or team B plays team A, does that change the game? No. Okay, so the order doesn't matter. There are 30 teams. I want to put them into groups of 2 essentially. And so 30 choose 2 is 435. Now, what if I want to play everybody 3 times? Well, I just take that and multiply it by 3. So that would be 1,305 games, which is one heck of a tournament. That's why divisions don't end up playing everybody all the time. Okay, at a 21 Pilots addiction meeting, there are 300 handshakes. How many people are at the meeting if every person shakes every other person's hand once? Okay, shake my hand. Thanks. How many people does it take to shake a hand? 2. Does whether I shook your hand or you shook my hand change the fact that me and you just shook hands? No. So the order doesn't matter. Okay, changing the order doesn't produce a different result. So this is a combination question. What I don't know is the total people. So that's my n value, right? I know that I'm selecting 2 at a time because it takes 2 people to shake hands. And I know there's 300 handshakes. So what I know is n choose 2 equals 300. So now I'm going to go to my formula sheet. N choose 2, I'm going to break that down into what the formula says, which would be n factorial over n minus 2 factorial equals 300. Now there's a couple things we want to do. You'll remember this from when we introduced factorials. N is bigger than n minus 2, so we're going to break n down until it comes to n minus 2. We'll stop there, put our factorial sign back so that our factorials divide each other out. The other thing I'm going to have to do in this one is I need to get rid of this 2 factorial. Remember though, 2 factorial is just 2. So I'll just multiply both sides by 2 and that'll get rid of that guy for me. So that's what I did in this next step. I expanded n. N, what comes before n is n minus 1. What comes before n minus 1 is n minus 2. That's where I want to stop. So I put my factorial sign back. And then the 600 appeared because I multiplied both sides by 2 factorial, which was 2. Now, my n minus 2's divide each other out. I have n times n, which is n squared. And I have n times -1, which is negative n. And you can see that I'm about to get a quadratic here. Bring my 600 over. And I have n squared minus n minus 600 equals 0. So now you want to go factor that. I'll give you a second to find me two numbers that multiply together to give me negative 600 and add together to give me negative 1. They are n minus 25 times n plus 24, which means n is negative 24 and 25. But then you're going to tell me, hey, wait a second, Hill, n can't be negative 24 because n has to be positive and it has to be greater than 2 and it has to be a member of the natural family. So n has to be 25. There are 25 poor addicted souls. Okay, awesome. So there's your mission, should you choose to complete it, and you have to. Have fun, and come see me with any questions you have. In the meantime, have a fantastic day. Take care, guys. Bye-bye.